Hello and welcome to Chem 120. My name is Dr. Tullis and I am going to be guiding you through this semester. We're starting right off with Chapter 1, the basics of chemistry. First learning objective for Section 1 is to recognize the difference between a hypothesis and a theory and understand how laws are established. So chemistry is about change. It was once only about changing one natural substance into another. Wood and oil burn. Grape juice turns into wine. Cinnabar, right here, this red mineral, ultimately changes into shiny quicksilver, this mercury when it's heated. As you'll see in modern chemistry, we now picture an exciting world of sub-microscopic atoms and molecules that interact with one another. We've also developed ways to predict whether or not a particular reaction may occur. Here's a reaction right here where I have sodium and I have chlorine, and they react to form sodium chloride, which is this salt. The emphasis was largely on finding a recipe to carry out a desired change with little understanding of the underlying structure of the materials or the explanations for why particular changes occurred. Chemistry is still about change, but now chemists focus on the change of one pure substance, whether it's natural or synthetic, into another and on understanding that change. So what is chemistry? Chemistry is a study of the composition, the structure, the properties, and the change of matter and energy. Well, what is matter? Hopefully you remember back from previous science classes that matter is anything that has mass and takes up space. And energy is the ability to do work. Chemistry deals with the study of elements, atoms, molecules, compounds, ions, and their chemical composition, characteristics, structures, and reactions. Chemistry also studies the chemical interactions, like bonding, between elements, atoms, and molecules. Look at all of the pieces of chemistry. There's organic chemistry, inorganic, physical chemistry, biochemistry, nuclear, polymer, environmental, analytical. Everything is chemistry. Why should you study chemistry? Well, although chemistry is endlessly fascinating, at least to chemists, why should you study chemistry? Each person probably has a different answer, but many students take chemistry because someone else has decided that it's an important part of preparing for a particular career. Chemistry is especially useful because it is central to our understanding of disciplines as diverse as biology, geology, materials science, medicine, physics, and some branches of engineering. Chemistry also plays a major role in the economy of developed nations, and chemistry and chemicals affect our daily lives in a wide variety of ways. A course in chemistry can also help you see how a scientist thinks about the world and how to solve problems. The knowledge and skills developed in such a course will benefit you in many career paths. It will help you become a better informed citizen in a world that is becoming technologically more complex and more interesting. And if you think about it, look, chemistry is everywhere in the world around you. It's in the food that you eat, the clothes that you wear, the water that you drink, the medicines you use, in air, in cleaners, you name it. It helps us ask questions like, why do the leaves change color in the fall? Why are plants green? How is the cheese made? Having a basic knowledge of chemistry is going to help you to understand product labels. Think about all the product labels in the food that you eat. Helps you make informed decisions, teaches you useful skills, how to solve problems. If there's anything I want you to walk away with from this class is better problem-solving skills. And chemistry opens up so many career options. I know I just mentioned a few, but you can look at the analytical skills that you're going to gain in chemistry. Chemistry applies to the food industry, retail sales, transportation, art, really any type of work that you can name. Let's talk about the scientific method. This is the term for an investigation that entails performing an experiment, proposing a hypothesis, testing the hypothesis, and then stating a theory or a law. As scientists, we study questions of our own choosings or one that someone else proposes in the hopes of finding an answer, discovering some useful information. The scientists formed a hypothesis, which is a tentative explanation or prediction in accord with current knowledge. Now, after formulating one or more hypotheses, scientists perform experiments designed to give results that confirm or invalidate these hypotheses. Now, in chemistry, this usually requires both quantitative and qualitative information to be collected. Quantitative information is numerical data, such as the mass of a substance or the temperature at which it melts. Qualitative information consists of non-numerical observations, such as the color of a substance or its physical appearance. Now, after numerous experiments by many scientists over an extended period of time, these results have been summarized as a law, a concise verbal or mathematical statement of a behavior or a relation that seems always to be the same under the same conditions. We base much of what we do in science on laws because they help us predict what may occur under a new set of circumstances. For example, we know from experience that if the chemical element sodium comes into contact with water, a violent reaction recurs and new substances are formed. And we know that the mass of the substance produced in the reaction is exactly the same as the mass of sodium and water used in the reaction. So that is, the mass is always conserved in chemical reactions, which is the law of conservation of matter. Once enough reproducible experiments have been conducted and experimental results have been generalized as a law or a general rule, it may be possible to conceive a theory to explain the observation. A theory is a well-tested, unifying principle that explains a body of facts and the laws based on them. It's capable of suggesting new hypotheses that can be tested experimentally. Sometimes, non-scientists use the word theory to imply that someone has made a guess and that an idea is not yet substantiated. To scientists, however, a theory is based on carefully determined and reproducible evidence. Theories are the cornerstone of our understanding of the natural world at any given time. Remember, though, that theories are inventions of the human mind. Theories can and do change as new facts are uncovered. Scientists, including chemists, have several goals. Two of these are prediction and control. We do experiments and look for generalities because we want to be able to predict what may occur under other circumstances. We also want to know how we might control the outcome of a chemical reaction or process. Understanding and explaining are two other important goals. We know, for example, that certain elements, such as sodium, react vigorously with water. But why should this be true? To explain and to understand this, we need a background in chemical concepts. Let's talk about some dilemmas and integrity in science. You may think research in science is pretty straightforward. You do experiments, you collect information, you draw a conclusion, but research is seldom that easy. Frustrations and disappointments are common enough and results can be inconclusive. Experiments often contain some level of uncertainty and contradictory data can be collected. For example, suppose you do an experiment expecting to find a direct relation between two experimental quantities. You collect 6 data sets. When you plot it on a graph, 4 of the sets lie on a straight line, but the others lie far away from the straight line. Should you ignore the last 2 sets of data, or should you do more experiments when you know the time they will take will mean someone else could publish their results first and thus get the credit for a new scientific principle? Or should you consider that the 2 points not on the line might indicate that your original hypothesis is wrong and that you'll have to abandon a favorite idea you have worked on for many months? Scientists have a responsibility to remain objective in these situations, but sometimes it's hard to do. It's important to remember that a scientist is subject to the same moral pressures and dilemmas as any other person. To help ensure integrity in science, some simple principles have emerged over time that guide scientific practice. Experimental results should be reproducible. Furthermore, these results should be reported in the scientific literature in enough detail so that they can be used or reproduced by others. Research reports should be reviewed before publication by experts in the field to make sure that the experiments have been conducted properly and that the conclusions are logical. Conclusions should be reasonable and unbiased, and credit should be given where it is due. This next section is about sustainability in green chemistry. You're going to understand the principles of green chemistry. I realize there is a ton of information on this screen, but let's first look at this first bullet here. The world's population is about 7.5 billion people, with about 80 million added per year. Think about this. Each new person needs shelter, food, medical care, and each uses increasingly scarce resources like fresh water and energy, and each produces byproducts in the act of living and working that can affect our environment. With such a large population, these individual effects can have large consequences for our planet. The focus of scientists, planners, and politicians is increasingly turning into a concept of sustainable development. Much of the increase of life expectancy and quality of life, at least in the developed world, is derived from advances in science. But we have paid an environmental price for it, with increases in gases such as nitrogen oxides and sulfur oxides in the atmosphere, acid rain falling in many parts of the world, and waste pharmaceuticals entering the water supply. Among many others, chemists are seeking answers to these problems, and one response has been to practice green chemistry. This green chemistry concept began to take root more than 20 years ago and is now leading to new ways of doing things and to lower pollutant levels. One chemist said, on one hand, society, governments, and industry seek economic growth to create greater value, new jobs, and more enjoyable and fulfilling lifestyle. Yet, on the other, regulators, environmentalists, and citizens of the globe demand that we do so with sustainable development, meeting today's global economic and environmental needs while preserving the options of future generations to meet theirs. How do nations resolve these potentially conflicting goals? Another scientist stated that it's better to prevent waste than to treat or clean up waste after it has been formed. Chemists are working on different synthetic methods that should be designed to use and generate substances that possess little or no toxicity to human health or the environment. Chemical products should be designed to function effectively while still reducing toxicity to the environment. Energy requirements should be recognized for their environmental and economic impacts and should be minimized. Synthetic methods should be conducted at ambient temperatures and pressures. And raw materials should be renewable whenever technically and economically practical. Chemical products should be designed so that at the end of their function, they do not persist in the environment or break down into dangerous products. So as you read over this section, you will be reminded of these principles and others and how they can be applied. And as you can see, they're simple ideas. The challenge is to put them into practice. Now we're going to get into the nitty-gritty of classifying matter. This chapter begins our discussion of how chemists think about science in general and about matter in particular. After looking at a way to classify matter, we will turn to some basic ideas about elements, atoms, compounds, and molecules and describe how chemists characterize these building blocks of matter. First, we're going to look at the states of matter and the kinetic-molecular theory. An easily observed property of matter is its state. That is, whether a substance is a solid, a liquid, or a gas. You recognize a material as a solid here because it has a rigid shape and a fixed volume that changes little as temperature and pressure changes. Like solids, liquids here have a fixed volume, but a liquid is fluid. It takes on the shape of its container and it has no definite shape of its own. Gases are fluid as well, but the volume of a gas is determined by the size of its container. The volume of a gas varies more than the volume of a liquid with changes in temperature and pressure. Let's start looking a little bit closer at the solid. At low enough temperatures, virtually all matter is found in the solid state. As the temperature is raised, solids usually melt to form liquids. Eventually, if the temperature is high enough, liquids evaporate to form gases. Volume changes typically accompany changes in state. For a given mass of a material, there is usually a small increase in volume on melting, water being a significant exception, and then a large increase in volume occurs upon evaporation. Let's look at solids a little bit more closely. Notice that it has a definite shape. We can see those atoms lined up in a beautiful shape, has a definite volume, and we have low Ke. That means kinetic energy. The kinetic-molecular theory of matter helps us to interpret the properties of solids, liquids, and gases. According to this theory, all matter consists of extremely tiny particles, atoms, molecules, or ions, in constant motion. So in solids, particles are packed closely together, usually in that regular pattern like that picture shows. and the particles vibrate back and forth within that average position, but seldom do particles in a solid squeeze past their intermediate neighbors to come into contact with a new set of particles. They're just barely vibrating back and forth. They're rigid and has a fixed shape. Now let's look at the liquid properties. We can see that it has an indefinite shape. Look at these molecules, how different they are from a solid. It has a definite volume. Now this is middle kinetic energy. The particles in liquids are arranged randomly rather than the regular pattern form in the solid. Liquids are fluid, like we said gases are fluid, because the particles are not confined to specific locations and can move past one another, so that it has more kinetic energy than a solid does. Now let's look at a gas. We said that its shape is indefinite. It fills its container. The volume is indefinite, depends on the container, and it has high kinetic energy. Now under normal conditions, the particles in a gas are far apart. Gas molecules move extremely rapidly, so they have really high kinetic energy. The molecules of a gas fly about, colliding with one another and with the container walls. This random motion allows gas molecules to fill their container, so the volume of the gas sample is the volume of the container. Now, with all of these states of matter, with solids, liquids, and gases, there are net forces of attraction between particles in all of these states, but it's generally small in gases and larger in liquids and even larger in solids. These forces have a significant role in determining the properties of matter. Here's just another pictorial way of showing the difference of how we can look at ice, which is a solid. We can see how rigid these particles are. This is solid ice. And melt ice. So we add energy to it because we said this was low energy, low Ke. This was medium Ke. So in order to go from low to medium, we have to add energy to melt it. And we can see the difference in arrangements of these particles. And then if I want to go from liquid water into gas water, it has to evaporate or vaporize. And so again, we have to add more energy to it. Now we can go the other direction. If I have water vapor as a gas, I have to remove energy to condense it into liquid water and remove more energy to freeze it. So we go from high kinetic energy to low kinetic energy. In order to do that, we have to get rid of energy. It's kind of like you're telling a kid, calm down. If they're bouncing off the walls, they have to release that energy in order to go from high energy to low energy. And we can see over here to the left, we can look at bromine. Bromine as a solid, as a liquid, and as a gas. Continuing on with the kinetic molecular theory, an important aspect, think about this. The higher the temperature, the faster the particles move. And there is a force of attraction that has to be overcome between particles in order to go from a solid to a liquid. There's a force of attraction that has to be overcome in order for that to happen. A solid melts to form a liquid when the temperature of the solid is raised to the point at which the particles vibrate fast enough and far enough to push one another out of the way and move out of that regularly spaced positions. And then as we increase temperature even more, the particles can go from a liquid to a gas. So the particles move faster and faster and faster until finally they can escape the clutches of their neighbors and enter that gas state. We are going to look at how to represent matter 3 different ways. The first way is the macroscopic. The characteristic properties of gases, liquids, and solids can be observed by the unaided human senses. They're determined by using samples of matter large enough to be seen, measured, and handled. You can determine, for example, the color of a substance, whether it dissolves in water, whether it conducts electricity, if it reacts with oxygen. Observations such as these generally take place in the macroscopic world of chemistry. This is the world of experiments and observations. This is our world of observing. And like we said, when we are making observations in the lab, there's qualitative and there's quantitative measurements. Qualitative measurements is non-numerical. We're using our five senses, like describing what color it is, what its appearance looks like, using statements like large or small, stating if something is hot or cold without specifying a temperature, identifying something by its smell, but it's not measurement. Like, I could say that this was a blue granular solid. That would be a qualitative measurement. Versus a quantitative measurement. We're using numerical data. We're giving a quantity with units such as mass, time, distance, temperature, the melting point, the density, the color that is specified as a wavelength, like saying that it was not just yellow, but it had a wavelength of 470 nanometers. As we can see, our quantitative measurement of this blue granule solid, we can say it has a mass of 28.331 grams. Now let's move on to the level of atoms, molecules, and ions, a world of chemistry that we cannot see, the particulate level. Take a microscopic sample of material and divide it again and again, past the point where the amount of sample can be seen with the naked eye, past the point where it can be seen using an optical microscope. Eventually you reach the level of individual particles that make up all matter, a level that chemists refer to as the submicroscopic or particulate world of atoms and molecules. Chemists are interested in the structure of matter at this particulate level. Atoms, molecules, and ions cannot be seen in the same way that one views the macroscopic world, but they're no less real. Chemists imagine what atoms must look like and how they might fit together to form molecules. They create models to represent atoms and molecules, where tiny spheres are used to represent atoms, and then use these models to think about chemistry and to explain the observations they have made about the macroscopic world. For example, looking at the particulate level here, our microscopic vision, we can't see these individual particles, not even with the microscope. But chemists often think about chemistry at the particulate level, and so as you can see here, we use spheres representing atoms. And we'll get more into this when we talk about periodic trends, but we can see here that here's our lithium atom, and over here we've got boron and carbon and nitrogen and oxygen and fluorine and neon. And we can see that as we go to the right in our periodic table, that our radius or the size of our atom gets smaller. And of course we'll be able to explain why that happens. And we can also see that as I go look at hydrogen and lithium and sodium and potassium, and as I go down groups or families, that my spheres get bigger. And we can discuss why that happens as well in a further chapter, but this is our particulate. This is our representation of our atoms at the particulate level. Then we have our symbolic level. Chemists carry out experiments at the macroscopic level, but they think about chemistry at the particulate level. They then write down their observations as symbols. The formulas such as H2O for water, or NH3 for ammonia, or NaCl, sodium chloride, for salt. The drawings that represent the elements and compounds involved. This is a useful perspective that will help you as you study chemistry. Indeed, one of our goals is to help you make the connections in your own mind among the symbolic, the particulate, and the macroscopic world of chemistry. But this is our written language of chemistry. Our written language of chemistry comes from none other but our periodic table. This is our symbolic. And this periodic table is going to be a useful tool throughout our whole semester. You will have this for every assignment and quiz and test, and you will always have this at your disposal. Moving on to classifying matter. We have a chemist. A chemist looks at a glass of drinking water and sees a liquid. This liquid could be the pure chemical compound of water, H2O. However, it's also possible that the liquid is actually a homogeneous mixture of water and a dissolved substance. That is, it's a solution. Specifically, we can classify a sample of matter as either being a pure substance or a mixture. So matter, right here, matter can be either a pure substance or a mixture. That's the two ways we can classify matter. A pure substance has a set of unique properties by which it can be recognized. Pure water, for example, is colorless and odorless. If you want to identify a substance conclusively as water, however, you would have to examine its properties more carefully and compare them against the known properties of pure water. The melting point and boiling point serve the purpose well here. If you could show that the substance melts at 0 degrees Celsius and it boils at 100 degrees Celsius at atmospheric pressure, you could be certain it's water. No other known substance melts and boils at precisely those temperatures. A second feature of a pure substance is that it cannot be separated into two or more different species by any physical technique at ordinary temperatures. If it could be separated, our sample would be classified as a mixture. So let's look further into what a pure substance can be. A pure substance, like we said, are composed of only one substance that cannot be physically separated. They have well-defined physical and chemical properties. So matter, like we said, can be a pure substance or a mixture. I'm going to go back to one slide. Pure substances or mixtures is what we can classify matter. But we can then be even more specific. So pure substance is a fixed composition, cannot be further purified. I'm going to skip ahead here and talk more about pure substances and then come back to mixtures. Let's say we have a pure substance. We can have within a pure substance either an element or a compound. When we go back and we say, all right, I've got matter and it's a pure substance, I've got to be more specific. Well, is it a compound or is it an element? So compounds and elements are pure substances. What's an element? What's a compound? Well, an element is a pure substance that cannot be broken down into simpler substances. Pretty much. Can you find it on the periodic table? An element consists of one type of atom. They cannot be decomposed or further simplified by ordinary means. Gold, Au, phosphorus, oxygen, even if it's diatomic oxygen, O2, copper, even if it was S8, it is just sulfur. Even though there's 8 sulfurs, it is an element. Now a compound is a pure substance, again, because pure substances are elements or compounds. Compounds can be broken down into 2 or more elements by chemical changes. For example, H2O. I can take water and I can chemically separate H2O into hydrogen gas and oxygen gas. It's not going to be a physical change, right? If I let liquid water sit out, it can evaporate, but it will evaporate into gaseous water. So it has to be a chemical change to make water turn into hydrogen gas and oxygen gas. Same with C6H12O6, that's a type of sugar. Silver chloride, another type of sugar. Carbon dioxide, salt. The properties of compounds are different from the uncombined elements that make it up. Let's look at our other part of matter. So we've covered this half of pure substances, and our pure substance can be an element or a compound. But what if we have matter that's a mixture? A mixture that is more than one pure substance, and the composition can be varied. We can have a heterogeneous mixture, or we can have a homogeneous mixture. Mixtures are composed of more than one substance that can be physically separated into its component substances. So let's look at what types of mixtures we can have. We can have a homogeneous mixture, which means we have a uniform composition, or a heterogeneous mixture, which means non-uniform composition. We can see here we have 2 different types of mixtures. We have a heterogeneous mixture, non-uniform. We have a homogeneous mixture. This is a solution that has salt dissolved in water. A homogeneous mixture consists of 2 or more substances in the same phase. So if I have salt dissolved in water, that means that I have a salt-water solution. No amount of optical magnification will reveal a homogeneous mixture to have different properties in different regions. If I were to have Gatorade, a jug of Gatorade, and pour 2 glasses of Gatorade, they are going to taste equally the same. One is not going to be different from the other. A heterogeneous mixture does not have uniform composition. Its components are easily visually distinguishable. When separated, the components of both types of mixtures yields pure substances and are said to be purified. Again, when we separate mixtures, because a mixture is simply more than one pure substance combined. Now, the efforts at separation are often not complete in a single step, however, and repetition almost always gives an increasingly pure substance. Here's some more examples of mixtures. Homogeneous mixtures. We can have tap water, olive oil, brewed tea, whiskey, laundry detergent, stainless steel, a cup of hot chocolate, hand sanitizer, shampoo, perfume, pudding. All of these are examples of homogeneous mixtures. Again, they are mixed together well enough to dissolve and appear as one substance. Some other examples: air, which is mostly a mixture of nitrogen and oxygen gases; gasoline, which is a mixture of carbon and hydrogen containing compounds called hydrocarbons; Kool-Aid is an example of a homogeneous mixture, and like we said, salt and water. An alloy is also an example of a homogeneous mixture. Two or more metals, like gold, silver, and copper metals, all combined together to create a 10 karat, 14 karat, 18 karat gold. So those are homogeneous. Let's say we have a heterogeneous, a mixture that has two or more pure substances that can be separated by physical techniques. In a heterogeneous mixture, the uneven texture of the material can often be detected by the naked eye. However, keep in mind that there are heterogeneous mixtures that may not appear completely uniform, but on closer examination, they're not. Milk, for example, appears smooth in texture to the unaided eye, but magnification would reveal fat and protein globules within the liquid. In a heterogeneous mixture, the properties in one region are different from those in another region. Let's talk about how to separate some mixtures. Heterogeneous mixtures can be separated by filtration. Look at this. We have a heterogeneous mixture of soil and water. When it's poured through filter paper, the soil particles are going to be trapped in the filter paper, and the water is going to pass through. So then we have more than one pure substance. Here's some other ways of separating mixtures. We can separate based on physical properties. If I have two liquids, let's say oil and water, so they have different densities, we can decant or centrifuge them. We can have two liquids mixed together. We can separate by its boiling point. That would be a homogeneous mixture. Let's say I had alcohol and water together. They have different boiling points, so I could heat them up, and the alcohol is going to have a lower boiling point, so we would heat off or boil off the alcohol, and we would be left with the water, so we could separate the mixture that way. We can separate it by the state of matter it's in, by intermolecular forces, by magnetism. Let's say over here I've got an example of a mixture, and I was able to simply take a magnet and get the iron filings separated from that mixture.